We are going to talk about electrochemistry, chapter 19. Before we do it, we need to talk about something that we have learned from Chem 1 class in chapter 3. That is what we call the redox reaction, short for oxidation reduction reaction. This is a type of reaction in which electron transfer from one reactant to another. Here we're going to use copper-zinc reaction to illustrate this process. In this process, copper gains 2 electrons from zinc. As you can see, copper from 2 plus to 0 charge. So it gains 2 electrons. This process actually is called reduction. And this is what we call reduction half reaction, in which you can see electrons as a role of a reactant. Oxidation reaction is what the zinc undergoes, because zinc from 0 to the 2 plus charge, and zinc loses 2 electrons. Since it loses electrons, we understand it undergoes oxidation reaction. And we can see we got ourselves an oxidation half reaction. Understanding half reaction is important to grasp the key concepts and skills in this chapter. In order for us to recognize or remember which process is doing what to electrons, so here I use these 2 acronyms to help us to understand, to remember what process is which. Oil rig. Oil stands for oxidation is lose. Rig stands for reduction is gain, of course, electrons. In chapter 3, we also talk about agents. Agents are the reactants and reactants, period. It cannot be switched to any other substances like products. However, there's something that's a little bit confusing, because when we say oxidizing agent, it is the reactant in which the element or the ion gains electron. So for example, we talk about oxidizing agent, we realize it's a copper, and copper is the reactant, as you see. For the reducing agent, it is the reactant in which the ion or the atom loses electron. So zinc and zinc. So one more thing I'd like to emphasize here. Oxidizing agent undergoes the opposite process. That means oxidizing agent oxidizes something. By oxidizing, it gains electrons. It is reduced. Vice versa for the reducing agent as well. If you want to build up a map by having reduction, reduced, oxidation, oxidized all together, so we have reduction, which is reduced, acronym, rig, oxidizing, which is oil, oxidized, they're all in a different line. And we can put reducing agent, oxidizing agent on the same lines as reduction and oxidation. We realize the lines are crossed. Why the line crossed? Because reducing agent undergoes oxidation reaction. And some ion or the atoms are oxidized. Vice versa for the other one. So this is something that we need to know about before we talk about this chapter, because they become fundamentals in chapter 19. Let's talk about a half reaction. Half reaction is a reaction in which loss or gain electron becomes quite obvious, and we emphasize on this part. Because when we write up the chemical equation, there's no place to show electrons. They are about ions, atoms, species, but no place for electrons. So that is the reason why we split the overall reaction into the half reactions, particularly for the redox reaction, so that we know which species undergoes what kind of process by having electrons as a part of either reactant or the product. So this is the function of half reactions. Oxidation half reaction, as we already discussed, it is a reaction in which the reactant loses electrons. Loses means minus. But in chemistry, we do not like minus. Because when we talk about equations, that's going to be something plus something yields something plus something. We do not like a negative sign or the minus sign in the half reaction or any other equation. So that is the reason why we are going to add 2 electrons on both sides so that we can have zinc yields zinc 2 plus 2 electrons. Here, electrons shows as the product. This is an important concept I want you guys to understand, because later on we're going to keep on discussing this. So once we realize it's oxidation, where are we going to put electrons? Electrons are going to be on the product side in this half reaction. It is very important for us to recognize where this 2 electrons is at. For the product side, that means oxidation. And so we'll see for the reduction here, this is a reaction in which reactant gains electrons, copper gains electrons. Remember, in the thermochemistry, we said gain means plus. All right. So this is how we put electrons on one side of a reaction or equation to show electron actually act as the reactant or the product in these half reactions. And then we will know, depending on the side of electrons on, what process is going to be. Half reactions could be conceptual. That means we do not have to physically divide the entire reactions into the half reactions in physical states or physical instruments or setups. But we can sometimes just imagine these 2 half reactions that constitute the entire or the overall reaction. But in some cases, we can actually physically separate these 2 half reactions. And we're going to see that later on as we discuss those features of cells or batteries. One of the important characteristics about half reactions is half reactions has to be balanced on its own. So which means not only we need to get atoms or ions balanced, we also need to get a charge balanced as well. But for example, if on one side it is a zinc 0, right, because it's element. So if it's 0 charge on a zinc on one side, the other side, the total charge must be 0 as well. 2 plus 2 minus, it's a 0 charge. So charge has to be balanced on either side as well as atom balanced. However, for some complicated reactions like this one, chromate reacted with protons yield chromium 3 plus and 7 molecules of water. Where should we put the electrons in order to balance the charges? So here's the clue. We're going to add electrons on the more positive side. How do we know which side is more positive for us to add electrons? So what we can do here is to calculate how many charge we have on the left. Okay, so let me get the 6 electrons out of the way so that we can, oh, I can't. So let's just calculate how many charges we have on the left without these 6 electrons. So there is a 1 species of the anion with a 2 minus charge. So that's 1 times 2 negative. So that's negative 2. 14 protons, total 14 plus charge. So negative 2 plus 14. So we have 12 plus charge. If we look at the right-hand side, we have a 2 times plus 3. And of course, the water is a neutral species, doesn't carry any charge, so it should be 0. So 2 times plus 3 is equal to plus 6. One side has plus 12 charge, the other side has plus 6 charges. We need to add electrons to the side with the more positive in order to balance the charge. So that is the reason why we add 6 electrons on the left. In this way, 12 can be offset by 6, so we have plus 6 on both sides. This is how we add up electrons in a Haber reaction to make the charge balanced on both sides. And of course, we actually feel it is more important if we have this word in opposite way. By balance the charges, we just know how many electrons is required and then where. Remember, if we have electrons on the left-hand side, what process do you think this one is? Reduction or oxidation? Right, this is reduction, because reduction here is the reaction in which reactant gains electrons. There's a plus electrons as the reactant. Let me erase the whole thing here because I'm making quite a mess. When we try to introduce the species that undergoes oxidation reduction, we put them all together to call them as reduced couple. For the reduced couple, we must have an oxidized species shown in the first place, reduced species in the second place, and we use a slash to connect these two. How do we know it? Which one is the oxidized species, which one is reduced species? We can set up the redox, so the Haber reaction to determine where we should add the electrons. And from where we should add electrons, we know which one is reduced species, which one is oxidized species. So for example, because I have dichromate on the same side of electrons, this one is what we call reduced, oxidized species, because it's oxidized, that is why it requires electrons to be reduced. And for the same reason, hydrogen needs to gain, so proton needs to gain one electron to become hydrogen gas or atomic hydrogen before it forms H2 molecule. So H plus is the oxidized species longing for electrons. One last thing I'd like to point out about a half reaction is with the same reduced couple, for example, zinc, right? So we have got a zinc and a zinc 2 plus for the same reduced couple. Oxidation and the reduction half reactions are mutually reversed each other. Here we have oxidation half reaction. We have oxidation half reaction on zinc because 2 electrons is on the product side. And we can write reduction half reaction on zinc where zinc 2 plus gains 2 electrons to become zinc. Now you realize these two are totally reversed each other. And of course, we have learned a lot of things about what happened if we have a reaction reversed, right? If you have a reaction reversed, we change the sign for delta H, we change the sign for delta G, we change the sign for delta S, and we also need to what? We need to do what to the equilibrium constant? Not just put negative sign in front of it, because remember, equilibrium constant cannot be negative. Indeed, what we have to do is take a reciprocal of this equilibrium constant. So therefore, I want you guys to understand, once we talk about a reaction being reversed, there's a lot of mathematical manipulation behind. And that is important because when we have those mathematics going on in this chapter, we need to remember those manipulations. One of the major applications for us to use these half reactions is to help us balance some complicated redox reactions. For some simple redox reactions, we can use the inspection method. For example, hydrogen reacts with oxygen to yield water. Everybody can balance the reaction using inspection method. Now for this type of reaction we have here, chromate reacts with oxalate to form carbon dioxide and chromium 3 plus. We need some help. So one of the approach to balance such redox reaction is to use half reactions. Of course, another approach to balance redox reaction is to use oxidation numbers. So here, I only discuss how to balance reactions using half reactions because that is sufficient to support the rest of the discussion in this chapter 19. The first step for us to balance this reaction according to the procedures layout, we need to write 2 unbalanced half reactions regarding species, which means we need to find some common atom in these 2 species to build up a half reaction. For example, chromium, carbon. So we got 2 half reactions. We do not switch positions. If Cr2O7 2 minus on the left, we put it on the left. If CO2 is on the right in its original reaction, we put a CO2 on the right. Next step, we balance atoms other than oxygen and hydrogen. Why? Because we're going to deal with the hydrogen and oxygen later when we have these keywords, acidic solution or basic solution. Now, we realize on one side that there's 2 chromate, so that is the reason why we add 2 as a coefficient in front of chromium 3+. Same reason, we add 2 in front of carbon dioxide so that we can have a chromium as well as carbon balanced in number of their atoms. In acidic solution, we understand that H plus is dominant. And once it's mentioned acidic solution, that means we need to add H plus to one side of reaction. And H plus react with OH minus to form water, right? In other words, H plus is going to react with oxygen to form water. That's the reason why we're going to add water on the other side. So here comes the procedure. We are going to add water to the side with the less oxygen. My preference is to determine H plus. So what I'm going to do is I'm going to add H plus to the side with the less hydrogen, or I'm going to add H plus to the side with the less positive charge, because H plus itself is positive charge. Then I'm going to add H2O on the other side. So once we realize which side we add H plus, which side we add H2O, we balance atoms. We balance atoms for this half reaction. Now let's check out this half reaction. I got a C2O4 on one side. On the other side, I got a CO2, 2 CO2s. Let's try to count the number of atoms. I find out atoms, so numbers of atoms of carbon, oxygen, they both balanced. Which means I do not have to add H plus anywhere. Because if I add H plus somewhere, the other side must be H2O. I do not have an extra amount of oxygen to form H2O with. So I'm going to leave this reaction alone, because this reaction is already balanced with regard to carbon as well as oxygen. Nothing needs to be added to this half reaction. I'm more interested in the first half reaction because I do see the difference in the number of oxygen. On one side, I have 7 oxygen. On the other side, I do not see any oxygen. According to this procedure, we are going to add water to the side with the less oxygen. Which side is less oxygen? This side. All right. And let's see if we can use adding protons to decide where we're going to add protons and where we're going to add water. We're going to add a proton to the side with the less hydrogen. Of course, I do not see any hydrogen there, so this probably doesn't work. But we can add hydrogen to the side with less positive charge. Which side has a less positive charge? This side, because this is 2 negative, this is 3 plus. We add protons to raise the number of positive charge. 2 out of the 3 statements usually should be satisfied before we decide where we add H plus. Remember, if we use the statement of H2O, we understand we're going to add H2O right here. If we want to add H plus, we understand we're going to add H plus here. So 2 of the 3 statements satisfied, we going to do just like that. So we add H2O on the right, and we add H plus on the left. Left because it requires more positive charge in order to have 3 plus. For the water, it's on the right hand side because we need some place to hold this extra amount of oxygen. Okay, how are we going to balance this equation? Apparently, there are 7 oxygen that are required to become a water molecule. Each water molecule has 2 hydrogen atoms. 7 oxygen atoms requires total 14 protons. And we need to put a 7 in front of the water. Now we have both half reactions balanced with regard of atoms. Chromium, oxygen, hydrogen, carbon. They're all balanced in their own half reactions. What's the next step? Next step is to balance the half reactions by adding electron to the side with a more positive charge. You notice the why I put this balanced atoms, balanced charges in bold. That is because these are the goals for us to balance, or we said the tasks for us to balance the redox reaction. As a matter of fact, you will see we're going to have a balance 3 things. We balance atoms as shown right here. We balance charge as we are about to do. In our next slides, you will see that we're going to balance electrons. All right. As we are discussed in previous slide, why we're going to have to add 6 electrons, because by adding 6 electrons, we have a +6 charge on both sides. Now, let's take a look at our second half reaction. Our second half reaction, we got a 2- charge, 0 charge as neutral molecule. We're going to add 2 electrons on the more positive side. 0, 2-, 0 is positive side, of course, so we can add 2 electrons right here. In this way, we got a 2- charge on either side in our second half reaction. And of course, the first half reaction is already balanced, and we have this discussed in previous slides. If you're interested, you can go back and take a look at it. By checking out the position of electrons, we should be able to realize which one is reduction, which one is oxidation. For the reduction, electron must be the reactant. And for oxidation, electron must be the product. So this is how we can use the half reaction to represent those processes, oxidation reduction, by checking out the position of the electron. So one last thing I'd like to point out before we leave this slide. For oxidation reaction, electron should be labeled as product. Always keep that in mind, because remember, we do not use minus in any part of our chemical equations. Electron as product is for oxidation reaction. Okay, our next step, as you can see, we balance electrons. So we have balanced electron in bold. So 3 tasks for us to balance in the redox reaction. Now we have those 2 balanced by their own half reactions. Well, between 6 electrons and 2 electrons, to which reaction should we multiply in order to make up 6 electrons? You got it. We're going to multiply 3 on the second half reaction in this way, so we can make 2 electrons into 6 electrons. Remember, those electrons are on the opposite side. So when we add up these two half reactions together, number of electrons should be canceled. Then we can do the rest to have this balanced redox reaction done. Now let's see. We have 3 reactants on the first half reaction. So that's 3 reactants on the first half reaction. And we have 3 oxalate. 3 oxalate. So we do the same thing on the other side of the equation. As you see, we got 2 chromium 7 water, 2 chromium 7 water, and we have 6 carbon dioxide, 6 carbon dioxide. And of course, you can see number of electrons cancel. Is there any other species we can cancel? Apparently, there isn't. So we put them all together. Okay. So this is a balanced redox reaction in acidic solution. Balanced redox reaction is quite important in this chapter because once we have the cell analyzed, once we have the half reaction all figured out, we need to report sometimes an overall redox reaction that represent what is going on in this cell or in the battery. So we here going to take 2 questions in our homework 14 as exercises. Okay, so here I just simply put up those questions, and then you're going to use the same format as you will see in homework 14. So I just hope that you can practice those process or those procedures and to get the redox reaction balanced. The first step, or the first question in that problem 1 here. Oh, by the way, in this problem, said it is an acidic solution, meaning we can add H plus somewhere. Nitrate is reduced to the gaseous NO, while HS minus hydrogen sulfide is oxidized to solid sulfur with H plus. From the wording, we can write the 2 half reaction. Because this is the first half reaction, this is the second half reaction. Although this reaction already tells us just what kind of a process that we have for each reaction, and later on we can check out whether they are correct, because eventually we're going to add electrons on one side of each this half reaction. We will know whether the species nitrate is reduced, HS minus is oxidized. Next question. Before the next question, so here I just highlight how and where we should add H plus and water for acidic solution, or OH minus and water for a basic solution. Since this acidic solution, so we cross out the second statement, second paragraph, and we're going to see that in our second question. The second question in this problem is, what are the coefficients of H plus and water in these 2 half reactions respectively? Let's look at the first half reaction. I got a nitrate and NO. To which side should I add H plus? Now let's see. When adding H plus for acid, this is my preference. H plus should be added to the side with a less overall positive charge. Which side has less overall positive charge? This side, right? because this side has negative charge. Needs H plus to balance other charge in order to have an O. Or the left side of H plus, it doesn't work because I do not have H anywhere in this equation. Or the side of more oxygen. That also indicates we're going to add H plus right here. So we add H plus on the left. Because remember, we got the 2 of the 3 statements satisfied. So this is a double check for us to add H plus. We're going to add H plus accordingly. So we add H plus on the left. On the right hand side, product side, there must be water. Just how are we going to balance this half reaction? Of course, you can just play the numbers, right? You play numbers for H2O, then H plus to find out just how many hydrogen and water that is required. But here, I'll try to let you know there's a shortcut. The shortcut is we can actually figure out the coefficient of H plus by checking out the number of difference of oxygen atoms. Alright, so let's see how it goes. I just want you guys to notice when we look at oxygen, before we add the coefficients to the water, on one side I got 3 oxygen, on the other side I got 1 oxygen. The difference of number of oxygen is 2, 3 minus 1, so the total number of hydrogen must be 4 because it's going to be twice as much. How? The stoichiometry of hydrogen and oxygen and water is 2 to 1. It is required that we need 4 protons in order to make up 2 molecules of water. And of course, you can double check to see whether we got the number of oxygen atoms balanced. 3 oxygen on the left, 1 plus 2 times 1, which is 2, 1 plus 2, 3. So I just hope that you can use this equation to figure out the number of hydrogen or number of a proton, so we can balance the rest of the species in this half reaction. Speaking of second half reaction, as we noticed that not only we have hydrogen that is balanced, the sulfur is balanced, there's nothing else for us to do, because I got an equal number of H plus. There's no need for me to add extra H plus. We are going to leave the second half reaction alone. Remember, by adding H plus, its function is twofold. First, balance charge. Second, take away the oxygen. If there's no oxygen in second half reaction to be taken away, there's no need for us to add H plus. By the way, there's already H plus there. It is there because there's no oxygen, and you can think of it that way. So that is the reason why we cannot add extra H plus anywhere in this half reaction. Our next question is, how many electrons are added in order to balance the charge of these half reactions? Now let's look at our first half reaction. It has been balanced regarding atoms, not the charge yet. How do I know it? Because I can calculate just how many charge I have on the left. Remember, I got 4 H plus, right? So each H plus has positive 1 charge. I got 4 of those, so that's a 4 times plus 1. And I have 1 nitrate So 1 times -1 right here. So the total charge is +3 on the left. How about on the right? 0 charge. Because both species as product are neutral molecules. Now, to which side should we add electron? Reminding you, electron is negatively charged. I just hope you guys realize we're going to add electron to the more positive side. Later on, you're going to see the case that we're going to add the electron to the less negative side to make it more negative. Alright, so we're going to add an electron to the more positive side. That means in order to make up 0, how many negative do we need? And we need -3, of course. So +3 plus -3 equals to 0. Electron is one negative charge species. 3 times -1 means there's 3 electrons. That is going to be on the left. Because we need extra 3 negative charge on the left-hand side. So this is how we add 3 electrons on the left in order to make the charge on both sides balanced. Let's look at second half reaction. From the left, there's only -1 charge. From the right-hand side, there's +1 charge. Remember, we add electron to the more positive side in order to balance the charge. So just how many negative charge do we need? -2. +1 plus -2 equals -1. Indicating we're going to add 2 electrons on the right-hand side. In this way, we got the charge balanced. So we can report we can add 3 electrons on the reactant side of a first half reaction, 2 electrons on the product side of second half reaction. By the way, if we add electrons as a reactant, which process do you think? Yes, it is a redox reduction. And when we add electrons as product for second, that is oxidation, half reaction. So by checking out the position of electrons, we will know which reaction undergoes where. So that's why it says nitrate reduced to nitrogen monoxide, HS minus oxidized to sulfur. Remember, there are 3 tasks for us to balance a redox reaction. Balance atoms by adding H plus, water, or OH minus and water. Second, we need to balance charges by adding electrons on one side of half reaction. Third, we need to balance electrons. So that is why you see here we have number of electrons gained equals the number of electrons lost. So what are we going to do with these half reactions where either 3 electrons or 2 electrons as a part of reaction? The easiest way for us to do is we'll just turn the coefficient of an electron to the multiple for other half reaction. So 3 is the coefficient of electrons in the half reaction number 1. So it becomes the multiple of second half reaction. 2 is a coefficient of electrons in the second half reaction, now it becomes the multiple of the first half reaction. That is the simplest way for us to do. So sometimes we might find out, okay, so we need to reduce the overall redox reaction, then reduce it. But it would be a lot easier if we just switch the coefficients to become a multiple for the other half reaction. This way, that saves us a lot of time. All right. So now we realize what the multiples are. Finally, we are going to add these two half reactions all together to see what is overall balanced reaction look like. 3 times 2, 6 electrons. 3 times 2, 6 electrons. So we now know we can balance, we can cancel out those number of electrons. So those half reaction combined must be good after we multiply these numbers. 2 times 4 protons, so that would be 8. 2 times nitrate, that would be 2. 2 times nitrogen monoxide, that would be 2. And they're going to be 4 water molecules. That is exactly what we're going to do for the first half reaction. For second half reaction, I got a reactant 3 HS minus. So I add 3 HS minus, and I got 3 sulfur and 3 protons and 6 electrons. So I'm going to add it up on the product side. And 6 electrons cancel. What else should we do? And you realize that we got 3 protons and 8 protons. So these are something that we needed to do to get rid of protons on one side. Obviously, if we subtract the 3 protons on both sides, we can get rid of protons on one side. Here, the product side. So the overall reaction is going to be like this. So we only need 5 protons here. Okay, now let's look at second problem. Second problem is about the same reaction, but in a different solution. So here we talk about the basic solution. Again, we write up 2 balanced half reaction here, and we realize it is a balanced half reaction. How? Because number of nitrogens is balanced, and here we have a number of sulfur balanced. We don't have to worry about the oxygen, okay? Because it is our next step. We're gonna balance the oxygens as well as the hydrogens. Also, we introduce hydroxide and water. How do I know it? Because it's a basic solution. In the basic solution, hydroxide dominates. We cross out the first paragraph, and we're going to follow second paragraph. When we add OH minus should be added to the side with the less overall negative charge. Makes sense, right? Because OH minus has a negative charge, so we need to add OH minus to the negative side. So the less negative side. Which side should we add OH minus? Here. Well, let's check out. Okay, let's do the rest of the statement, hoping that we can have another statement satisfied. OH minus should be added to the side with the less oxygen. Apparently, this side is less oxygen. So no doubt, we're going to add OH minus on the right, because 2 of the 3 statements are satisfied. Water should be added in the opposite side of the equation. So this is where we add H2O on the left. Now that becomes even more difficult for us to balance this half reaction, because we got oxygen everywhere in every species, hydrogen, Yes. Okay, that's still going to be difficult. Of course, we can play the numbers, play the coefficients on the water and hydroxide, hoping that we can have this figure out. But again, there's a shortcut. Very similar to that of H+. Number for H- is twice the difference of the number of oxygen atoms in this half reaction. The one in black, the one before hydroxide and water are added. Again, as we see, if we put 1 as a subscript for the number of oxygen in the NO molecule, so that is 3, that is 2, so 3 minus 1 is 2, total number of hydroxide is required, 4. So we add 4 hydroxide on the right. Now remember, water is the only species that has hydrogen. 4 hydroxide results 2 water molecules. Then you can check out the number of atoms to see whether this equation is balanced. I got 2 water molecules, 2 oxygen, 3 oxygen here, so total 5 oxygen atoms on the left. Here, 5 oxygen atoms on the right. I got this equation balanced, nice and easy. All you need is to realize we got this equation to figure out the coefficient of hydroxide. All right, for second half reaction, there's nothing for us to do because sulfur is already balanced and there's no extra oxygen or hydrogen for us to balance. So we should not apply this statement on second half reaction. We just simply leave it alone. Our next step here is you already realize that we're going to add electrons on either of these half reactions. Again, let's calculate the charges on either side of this half reaction. Water molecule is 0 charged. So 2 times 0 plus 1 times -1. Remember, the coefficient that do not have, meaning the species has 1 as its coefficient. So 1 times -1, so that's -1 total. On the other hand, the other side, we got the 1 molecule is 0 charge and the 4 hydroxide is totally 4 negative charge. Adding up, we got -4. Now you realize that we're going to add an electron to the side of less negative charge. Which side is the less negative charge? Here. In other words, we make it more negative. Again, we need a 3 or -3 to make -4 so that it is equal to the number on the other side. -4 meaning 3 electrons on the left. What type of process do you think this reaction represents? Again, it's reduction. For second half reaction, obviously we're going to add the 2 electrons on the right. Although this calculation shows the same way, we add the 2 electrons on the right. The process this half reaction presents, oxidation. Remember, nitrate is reduced to nitrogen monoxide. Sulfide is reduced to solid sulfur. That is what is said in the question, of course. So the prediction of the question is correct as we now prove. Next question, we balance charges. Again, as you can see, coefficient of the electrons in one reaction becomes the multiple of the other reaction. And 2, coefficient of the electron in the second half reaction becomes the multiple of the first half reaction. In this way, we can add these 2 half reactions together because Now we realize we have 6 electrons in both half reactions. We can simply add the species all together. Multiply by 2, 6 electrons, 4 water, and 2 nitrates. So that's what we have here. And 3 sulfides. I'm sorry, so the product, so 2 nitrogen monoxide and 8 hydroxide. This is what we got here as a product. For second half reaction, we got 3 sulfide as a reactant and 3 sulfur and 6 electrons as product. 6 electrons cancel, and we find that there's nothing else for us to cancel, so we just simply copy the rest down. And that is the overall reaction, redox reaction. This is it for balancing the redox reaction. And here we use a half reaction as a guide for us to balance the redox reaction. In most of the cases, especially in an exam, we need to know which ion we should add if we have a solution. If acidic solution, we add H plus and water to the opposite side. For the basic solution, we add OH minus and water to the opposite sides of the half reaction. And remember what statement that guide us to add either H plus or OH minus. They're quite different, but sometimes once we analyze it, you'll find it's logical, because when we add hydroxide, it's pretty much the opposite to the statement for us to add H plus. Why? Because they have opposite charges. 3 tasks for us to go in order to balance half reactions. First, balance species. Even before we add H plus or water or OH minus and water, we need to balance the atoms other than oxygen and hydrogen. That becomes our very first step. Second step, we determine add H plus / water or OH minus / water. Then we balance all the atoms. Then we balance charges by adding electrons on one side of a half reaction, indicating which one's redox, which one's oxidation. If you find out that you end up adding electrons on the same side, something must be wrong. Third task is to balance electrons. The easiest way for us to do is switch the coefficients of electrons and let them become as the multiples of other half reactions. That is the easiest way to do. And sometimes you may find out, especially in a homework assignment 14, and you find out you may have to reduce the overall half reaction a little bit. And this is how we balance the redox reaction. Now, let's start with chapter 19 from the very beginning. This chapter is about electrochemistry. The definition of electrochemistry is chemistry study of the relationship between a chemical change and electrical energy. If we switch electrical energy with the heat, then that would be the thermal chemistry that we discussed in chapter 5. Of course, this is another chapter regarding the energy. Nowadays, electrochemistry have its application everywhere. So one of the popular example would be batteries. I just can't imagine how pathetic our life will be if there is no battery anymore. Of course, our goal here is try to replace petroleum with more cheaper or more environmental friendly fuel. So one thing for us to think about is using fuel cell. The same principle applies. Couple other more application for this electrochemistry industry is electrolysis. This is how we get aluminum, copper, so on and so forth. Corrosion is a major topic for United States Navy because we have to keep those ships in shape. So that is part of a reason, I think, is one of the major reasons why, okay, after 6 months in the sea, we need to call those aircraft carrier back to the port on the deck so that we can take care of this corrosion problem. Recently, electrode deposition becomes quite interesting because one of the typical examples will be those shiny surface in our iPhone. This all been done by electrode deposition. Of course, electrochemistry has its application in biology as well. So for example, photosynthesis or metabolism. As a matter of fact, in chemistry, we consider photosynthesis and metabolism as the opposite reaction. And there's electric current going on between the neurons, so nerve cells, so there'll be nerve impulse in the neurons, and some fish actually can use electricity to shock its prey, or as a self-defense, like electrical eels, all of which is a case or example of electrochemistry. There are 2 types of electrochemical cells that we're going to discuss. It is the galvanic cell we're going to discuss the most. Later on, we just give you a brief introduction of electrolytic cell. The galvanic cell actually is a prototype of all the batteries. And as you can see, this is a cell where people use the spontaneous oxidation reduction reaction to generate the electrical energy. For electrolytic cell, it is a non-spontaneous reaction. In order to make a non-spontaneous reaction to take place, remember, according to the chapter 18, there must be addition of external energy. Not only it has to be supplied and is supplied continuously. Both cells actually can be shown in one battery we called rechargeable battery. When it is charged, it is what we call the electrolytic cell. And when it's discharged, once we unplug the charging cord, it becomes the battery, which can be explained by the galvanic cell. Of course, I'd like to remind you, spontaneous process is the process where we see the delta G less than 0. For non-spontaneous, delta G is greater than 0. In this chapter, it also serves a purpose to review what we have learned from chapter 18. Well, for the rest of this lecture, we're going to focus on the features of a galvanic cell. In our second half of lecture, we're going to talk about the all calculations, characteristics of the cell or the battery. Speaking of features of these galvanic cells, one thing that's sticking out in front of us are those metal plates or metal rods. or we actually call them electrodes. Electrodes are the conductors through which electron current enters and leaves a cell. In this example, okay, so we have copper and zinc are reacted together, and as we already discussed, this is a redox reaction called electron transfer. So we can use electron transfer to generate the current to become a battery so that it can do work. So when it does work, we've got a lot of things going on. This particular setup is also called the Daniell cell because it's been done by the guy named called Daniell. And that was the setup. And this becomes the most popular example for all lecture courses when we discuss chapter 19 electrochemistry. All right, when we talk about electrodes, there is always going to be a pair. One is called anode, the other one is called cathode. Anode is where we see the negative sign in our battery. Cathode is the electrode that has the positive sign. This is what we have on the battery. But what is the chemistry behind them? What is the chemistry behind the anode, for example? Why it is negative? Negative means this side has electrons coming out. Electrons coming out, it means electron must be the product as the reaction produces electrons. When we look at this setup, which side do we realize, left or right, do we realize a oxidation half reaction, right? Because remember, electrons are produced, so that means electron as a product, so we are looking for an oxidation reaction. For oxidation reaction, in this setup, we realize we got a sulfur, a sulfate, sulfate, sulfate everywhere. That means sulfate actually is a spectator ion. We do not have to consider sulfate in this chemical reaction. Now let's look at this. Zinc, you see the arrow, yields 2 electrons, yields zinc 2+. Is that obvious enough for us to realize we got 2 electrons as a product from this half reaction? Electron as a product, as we already discussed, that is oxidation. Cathode. Cathode, since it's a positive, meaning electron, this is where electron is going to go in. Electron is going to go in and get reacted, consumed. Okay, so one beaker, we understand that this is the oxidation half reaction. The other beaker, that gotta be the reduction. How do I know it? Let's see. Here, I got a copper 2+, yield copper. 2 electrons, yield copper. Obviously, copper 2+ plus 2 electrons yields copper metal. Electron as a reactant, indicating we got a reduction half reaction going on. One last thing. Let's just see how this ions migrates. Why ion has to migrate? Because, as you can see here, as we got electron passing. By the way, zinc is the anode, so that means it has negative charge. And of copper, it is cathode, it has positive sign. And how those, this is how we see the electron flows from the anode to the cathode. But also, as I said, it is interesting for us to see just how those cations and anions in this setup migrates. And why the cation and anion have to migrate? Because, as you can see here, for this electrode, zinc, after losing 2 electrons, there's going to be zinc 2 plus generated or produced. And as the reaction goes, we're going to have more and more zinc 2 plus accumulated. So that is the reason why, in order to make a solution in neutral at all time, it calls for sulfate. It causes sulfate to migrate. As you can see, sulfate goes up, sulfate goes down on the other end, and sulfate come into the solution and to meet the zinc 2 plus. When we design a battery, it is very important to keep either side charge neutral, because we do not want a charge buildup, because charge buildup is going to hurt the battery and make a battery very short-lived. All right, so now as we can see, for the anode here, it calls for the anion sulfate. So this is where the anion migrates towards. And of course, for the cation, this is where the cation migrates towards in order to have the reaction done, because cation migrates to this electrode, copper, to get electrons to get reduced. From all of these explanations, which we have to remember all of them, it's become quite confusing, because anode, okay, electron is produced, oxidation is going to occur. What about the anion? So it would be very helpful if we can find something that is easy enough for us to remember just by one point, and we can derive the rest after that. So I just don't know if you ever realized anode, oxidation, both words starting with a vowel. So now we can make up a statement like reaction starting a vowel occurs on an electrode starting with a vowel. For anode, oxidation reaction. Once we have oxidation reaction, electron becomes product. This is where electron produced. Electron produced, anode. And more cation going into the solution requires anions migrates towards. See, everything else can be derived automatically with such logic once we realize just what type of reaction occurs on the anode. Starting with a vowel, oxidation. I just hope you can take a good advantage of that statement to link the type of a process to the electrode. We just have spent a lot of time talk about those electrodes. But the electrodes are not all by themselves. They go with, like in our case, beakers. Those beakers are actually called chambers or compartments. They are the same thing. but I usually call them chambers. In our diagram, we got two chambers. The chamber that I have anode in, we call it anode chamber. The one with the cathode in is called cathode chamber. In the chamber, we have electrode as well as the half reaction to take place. And in our case, we got anode, which is zinc. But we also realized zinc is a reactant as well, so that it can produce electrons. So zinc, not only acting as a reactant, it also acts as electrode, as an anode, because it's a piece of metal, conducts electricity. As this diagram shows, we have zinc dissolve in the solution as a zinc 2+, leave 2 electrons behind. And in our next lecture, we'll try to explain just how this electron can make a flow. In the cathode chamber, as you will see, copper here is also involved in the reaction, because there's going to be more copper deposit on its surface. So we start to see the gain of copper, because we got a copper solution, copper 2+, gains the electrons when it contact the surface of copper and form a copper metal, stick on the surface. And copper is a very good electrical conductor, so it itself also serves as an electrode, a cathode. And this is a place where electrons are consumed. If we have this reaction taking place for some time, this is what we have. We start to see more and more zinc dissolving and more copper produced. That, as a matter of fact, is a way for us to purify copper. As in nowadays, we need more and more chips, computer chips, to make a better computer, to make a better cell phone, and make a better circuit for a lot of other things. The purity of copper is highly demanded. This is the one way for us to get the copper up to 3 nines, 99.9%, which is not enough by the semiconductor industry. For semiconductor industry, it requires 7, or nowadays I believe it's going to be 9 nines. That means 99.99999. I don't know how many nines I already said. So there's going to be 9 nines. That means for every 10 billion atoms, there's only one atom that's not copper. All right. After we have talked about anode chamber, cathode chamber, there's one important piece that we also pay attention to. That is the salt bridge. This is the salt bridge. That's U-tube upside down. This U-tube is filled with a gel. The gel in which lies in a strong electrolyte. So in this salt bridge, you start to see the motion of the ions so that it can balance out the charge. So the salt bridge is a necessity, because without it, we are not going to have a so the closed circuit. Without a closed circuit, electron does not move. Electron does not move. We do not have a battery. People sometimes pay too much attention to those chambers and forgot about salt bridge. Salt bridge is equally important as the other two chambers. Without it, There's no battery, no functioning batteries ever. One way to talk about the galvanic cells without drawing too much of a picture is to use a shorthand notation. This is a shorthand notation that we can use to define a cell, and we also can address a lot of detailed information. In order to make up a cell, use this notation. The cell must be written in order of half reactions with the anode reaction first, which means we can divide this notation in two parts. On the left, there's going to be an anode half cell, which is anode chamber. On the right, that's going to be the cathode chamber. And I'd like to remind you, electron comes from anode going to the cathode. So that is reason why we have this electron flow set up from left to right. This is exactly how we write those species in this particular order. First, we write the electrode. Electrode, the anode, where the electron goes, so coming out. So where's the electron coming out? Coming out from the reduced species to oxidized species. For example, reduced species like copper metal, right? Oxidized species like copper 2+. So you realized reduced species has more electrons than oxidized species. You see electrons going in this direction. I want you guys to notice they are the same direction right here. The bar here represents the phase boundary. And of course, if we have a phase boundary like between solid and liquid, so we needed to get this thing up to let people understand, okay, so electrode should be the solid as always, and whatever that's in between here could be other phases like a gas or liquid or some kind of solid as well. But once we realize these two have a different states, there could be another bar in between, because bar tells us they are in different states. Once we list the electrode bar to separate solid from the rest of this state, for example, if that's liquid, so we need to measure the concentration sometimes if they're given. And after we list those reduced species, then followed by the oxidized species, that's pretty much it for all we have in the anode chamber. Here comes the salt bridge. The salt bridge here is a 2 dash line. This 2 dash line to solid line to tells us not only there's a phase change or the state change, and we talk about something into the different chamber. Alright, so once we talk about the species of cathode chamber, that becomes kind of like a mirror image. So what comes to the last becomes to the first in the cathode chamber. So oxidized species to the reduced species. Remember, oxidized species has less electrons. Reduced species has more electrons. So again, we start to see the electron flow, same as the electron flow as we talked about for the setting up of this shorthand notation. And through the phase boundary, we have another electrode, which is the cathode. So from this shorthand notation, we realize we have electrodes sealed up everything. In other words, at each end, we have a solid electrode material. Concentration are typically added in the parentheses to all solution species. It is quite important because Sometimes concentration can make the reaction go in the other direction, as we already discussed in our last chapter. Remember, okay, G6P to F6P, and the concentration can change the spontaneity of the reaction. That as well happens. So that is why we need sometimes mark the concentration to let people know. Okay, now let's take a look at that example. We have this setup, and we're going to consider this as a galvanic cell. So first, we need to think if there's anything missing in order to have a galvanic cell. And then here come the 3 more questions. As we go through the first question, we realize in order to have a battery, one thing that's for sure, we must have something to close the circuit. That something must be a salt bridge. That salt bridge must contain nitrate. Why nitrate? Because as you can see, we got nitrate everywhere in these 2 chambers. In other words, nitrate is a spectator ion. So there must be nitrate in the electrolyte of the salt bridge. And in order for us to realize which one is a cathode, which one is an anode, we can tell it by the electric flow. Electric flow actually tells us where the electron comes out, where the electron goes in. Electron going from right to the left, that means aluminum is where electrons coming out. Cobalt is where the electron goes in. Electron coming out makes aluminum as the electron source. Electron source, it must be the anode. And cobalt must be the cathode, of course. And this is how we can determine those electrodes. For those chambers, according to those species, we should be able to write up the half reactions for each chamber, then the cell reaction. Now let's look at the anode chamber and see what happens. For anode chamber, after we take off the nitrate, why 3 nitrate? Because there's aluminum 3 plus. Remember, solution must be neutral. So for each aluminum, there's going to be 3 nitrates to get the charge balanced. So after we cross out those nitrate, the species we have left is aluminum and aluminum 3 plus. So we realize these 2 becomes a reduced couple. The couple that gives or have something to do with the electrons transfer. As for anode, it is starting with A, right? Starting with a vowel, so that's oxidation. Once it's oxidation, so electrons must become the product. So once we have electrons as a product, the product side must be the aluminum 3 plus. Aluminum must be on the other side of the equation in order to get the charge balanced. Same reason. In order for us to determine just which side should we put the cation and the metal, we set up the position of the electrons first. For cathode, we understand it's reduction. Reduction will have electrons as a reactant. Since the left-hand side has already electrons negative charge, it has to be the cobalt 2 plus to get the charge balanced. Cobalt must be on the right-hand side to have the charge balanced. This is how we write up the half reactions. First, we put electrons in a certain side of this half reaction because we know what kind of a process or reaction occurred on these electrodes. Let's do that first. Then we determine just how we're going to organize those ions and neutral species. Okay, after we write up those two half equations, we realize that we have 2 electrons in one half reaction, 3 electrons in the other half reaction. That means we cannot just simply add these 2 half reactions together. We have to multiply each half reactions by the coefficients of the electrons from the other reaction. 3, 2. That leads us the cell reaction as such. The coefficient of aluminum is 2. The coefficient of cobalt is 3. And only in this way you start to see the charge has balanced. As you can see here, 3 times 2 plus, that's a 6 plus. 2 times 3 plus, that's a 6 plus. We have the atoms balanced, we also have the charge balanced. When we write up the shorthand notation of the cell, remember we start with the anode, with the electrode first, so that's why we have aluminum. That's it. And aluminum also is a reactant as we go into the chamber. So there is a phase difference, right? Solid to the liquid. So that's why we have the bar. And we write up aluminum 3 plus. And we need to let people understand this is AQ occurred in a solution. That's pretty much it, because we do not have to write so this nitrate, because it's a spectator ion. As we exhaust every species in this anode chamber, we go through the salt bridge where this double line indicates. And as we're going in, remember we start with oxidized species, because this is where the electrons gonna go after it's reactive. So after it's obtain or get electrons, becomes the reduced species. Cobalt, then the reduced species cobalt, which just happens to be an electrode. This is how we write this notation of the cell. Couple more exercise. For the first problem, as we try to label the anode and the cathode, same reason. Once we are given the electron flow, we understand iron must be negative, platinum must be positive, because negative is where the electrons coming out, cathode is where the electrons goes in. The iron strip now, as we know, this is anode. This is where you have the electrons coming out as a source. Aluminum, the platinum rod becomes the cathode. Second question, write up the balance, the equation for half reaction and cell reaction. And what happens for the anode chamber? As for anode chamber, we understand the anode has started with a vial. The half reaction must start with a vial as well. So we understand the anode undergoes oxidation. Oxidation meaning electrons as right product. So it's very important for us to set electron first in this half reaction. We understand electron must be the product for oxidation half reaction, so we put electrons on the right-hand side of this half reaction. Apparently, we see nitrate as the spectator ions because we got nitrate everywhere here. The only species in the solution is iron 2+. Iron 2+ must be the oxidized species because 2+ charge means electron deficient. It's gonna be on the right-hand side of the equation. On the other side, it must be iron. Once we have those couples or reduced couple located, we can balance this equation by putting 2 in front of electrons. Now we have this half reaction balanced in terms of atoms as well as the charges. Speaking of cathode, we understand it undergoes reduction. Reduction requires electrons as, of course, reactant. We put electrons on the right. As we can see, this is where iron 3+ is going to get reduced, right? Because it's a reduction. Iron 3 has the highest positive charge, so we put iron 3 on the left. Now we have to determine what is the reduced species of this iron. Another common ion with less positive charge is iron 2+. But for iron 2+, we understand it is in aqueous solution, but we do not see iron 2+ anywhere in the solution. By the way, how do I know iron 2+ is in the solution? Because of nitrate. Remember, any salt that has a nitrate as anion is soluble, according to what we learned in chapter 3, solubility rule. That is the base for us to write up this iron 2+. Iron 2 nitrate is soluble in the solution. We should be able to see iron 2+ in the solution, but we don't. That means iron 2+ is not the correct product for this half reaction. What is it then? There must be something solid like iron metal. So as it turned out, we got iron metal deposit on the platinum rod. That is why we do not see iron 2+ in the solution, because iron 3+ has been reduced all the way down to iron metal, which is out of this solution. Okay, let's balance this half reaction. So we have 3 electrons. And for overall reaction, we understand that we have to multiply multiply 3 on the first, 2 on the second, in order to have 6 electrons in either half reactions. And combine these 2 half reactions together. Now that we have 6 electrons in each, we got 3 iron. So that's a 3 iron. 3 Fe2+, 3 Fe2+, 2 iron 3+, 2 iron 3+, 2 Fe metal. And as we can see, we can subtract 2 iron metal on both sides. So this is the overall reaction we are getting. I just want to remind you again, it is not the iron 2 plus as the product of this reduction half reaction, because we do not see iron 2 plus in the solution. Why? Because it's nitrate. Any salt containing nitrate is considered as a soluble. Speaking of shorthand notation, we start with, of course, anode. We got iron serving as electrode as well. In the solution, we have iron 2 plus. There's a phase boundary between them, so iron Fe bar, iron 2 plus, skip the nitrate through the salt bridge. We have in the solution, which is iron 3 plus, and here I want you guys to notice we have iron deposit on the platinum. There's a phase boundary because we have a solid on surface of solid or coated on a solid. There's an edge that we can actually see. So please don't forget there's a boundary between the two solids. Our next example. Now we have a new setup of this galvanic cell. Electron flow tells us this time platinum is the anode, copper is the cathode, right? Because platinum is where the electron coming out. Copper is a cathode. Just what kind of reaction that takes place on the anode, which is the platinum? We understand that there is a reduced couple. Again, nitrate is something that we do not interested in because that's a spectral ion. And we have H plus, H2. Okay. Anode undergoes oxidation reaction, as you can see. This is the reaction. We are going to consider electron as a product, where we're going to put electrons on the product side. Now we have electron, that's negative charge on the right, between H plus and H2. Which one should we put on the same side as the electron? H plus, of course. And then we put H2 on the other side. And of course, that leaves 2 electrons for this equation to be balanced. For the cathode, undergoes reduction. This is the reaction. We see electrons as the reactant, so we put the electron on the left. When we look at the species, do not worry about nitrate. We have a copper 2 plus and a copper. Those two becomes a couple. To which side should we add a copper 2 plus? Left or the right? Left. Because plus minus, those charge can be cancelled, so that we can have a copper metal, which is charge neutral on the right. Requires 2 electrons to balance this half reaction as well. Both half reaction has 2 electrons, which means we can simply add these two together because we do not have to multiply or multiply both by 1. Means we do not multiply anything. And put them all together. So we have one hydrogen react with copper 2 plus, yields H2H plus, and copper metal. As we write up the shorthand notation, remember we start from here. When we start from here, first it's a platinum. Remember when we write from left to the right, so that is PT, and there's a bar And between H2 and H plus, we need to make sure that electron flow actually goes from left to the right, so from reduced to oxidized. Which one's reduced? Which one's oxidized? H plus is oxidized. This is where we have the electrons on the same side. And in this equation, copper 2 is oxidized, again, same side with the electron. Now we understand reduced species is H2, hydrogen is H plus, proton is oxidized. And here I just put up this 1 molar solution in aqueous, and this is gas at 1 atm because it's gas 1 atm. Once our setup gives us detailed information, we need to write into this notation. After we done with the species from the anode chamber, move on to the cathode chamber through the salt bridge. We got the copper and the copper. Copper is oxidized species, as we already discussed, the same side as electron, bar as phase boundary, and we got a copper serves as either reactant, as well as both reactant and the electrode as cathode. Okay, so in this half of this lecture, it takes almost 90 minutes. Okay, I'm sorry. I try to slow down this thing a little bit so that I can explain things in the more detail. So in this half, we learn how to balance the chemical equation, use half reactions. And we can use half reactions to determine which one is oxidation, which one is reduction, depending on where we put electrons in those equations. When we balance the redox reaction, we understand the 3 tasks that we have to perform. First, balance atoms. Second, balance charges. Third, balance electrons. As we talk about the features of the cells, I just want you guys to understand anode has oxidation reaction going on. The electrode starting with the vial has the reaction occurred starting with the vial. The anode has oxidation going, cathode has reduction going. And we can derive the rest based upon our statement. For anode, since it undergoes oxidation reaction, we understand electron as a product, so it has to be the source of electrons. And this is where the anion coming in to balance out the charges. For the cathode, it gains electrons, undergoes the reduction because electrons on the left-hand side of this half reaction as a reactant. And this is where we start to see the cation migrates towards. And speaking in writing the shorthand notation, remember we always start with electrode, start with anode, end with a cathode. Once we finish the anode chamber, we need to write 2 straight lines to make sure that it represents the salt bridge before we go to the cathode chamber. This is it for this half of the lecture. In our next lecture, our next half, and we're going to talk about the potentials, the free energies, and a whole bunch of calculations that's associated to those concepts. Thank you.